In this video, I'll explain what accumulation functions are and why they're so useful in calculus. Here is an example of an accumulation function. It looks like a definite integral, except there are two variables. T is used as an input to f, and x is used as the input to a and the upper bound of integration. You might be wondering, what is this and why is it useful? To start thinking about this, let's look at the behavior of an interesting creature. The crested platypus is a creature that lives in and around the deep lakes of New York State. When it is ready to mate, the male crested platypus enacts an interesting dance. As it dances, the platypus rapidly waves its crest, which causes it to levitate off the ground. To understand this levitation a little better, let's make a graph of its velocity in meters per second as a function of time, measured in seconds. We'll graph the velocity as we watch it levitate. Now that we have information about the velocity of the platypus, let's use it to get some information about how far the platypus levitates above the ground. Let's first set the value of x equal to 2, as shown by the red section of the graph. Thus, we'll be looking at the first 2 seconds of the platypus's motion. Now, we want to compute the platypus's amount of change of distance from its starting position over these first 2 seconds. To do this, we'll look at the velocity for each moment in time, multiply these values by small amounts of change in time, and then add these amounts up, starting at time 0 up to our value of x, which is 2. And when we let the value of t increase from 0 to 2, then the value of this definite integral is represented by the area between the t-axis and the graph of the velocity function, between t equals 0 and t equals 2. Next, let's increase the value of x from 2 to 4. This would change the upper bound of the definite integral to 4, because we'd now be considering the first 4 seconds of the platypus's motion. And when we let the value of t increase from 2 to 4, then the value of this definite integral is represented by the area between the t-axis and the graph of the velocity function, between t equals 0 and t equals 4. Next, let's increase the value of x from 4 to 6. This would change the upper bound of the definite integral to 6, because we'd now be considering the first 6 seconds of the platypus's motion. And when we let the value of t increase from 4 to 6, then the value of this definite integral is represented by the area between the t-axis and the graph of the velocity function. Now, we've computed the total accumulated distance at 3 different points in time, at 2, 4, and 6 seconds after the platypus started levitating. But we could have computed this for any point in time, which we show by writing an x in the upper bound of the definite integral. And we can think of this as a new type of function, the total accumulated distance function. Now, one thing that might look a little strange is that there are 2 variables, t and x. Both t and x are time variables, however, they serve different purposes. The x variable tells you that you're accumulating distance from 0 to x, and the t variable is used in the product of v of t times dt to compute the distance. Now, we can think about what the function d of x looks like. Here is a graph of v of t in red, and we'll graph d of x in purple as both the accumulating area and as a curve. In this graph, we can see that we are accumulating distance quickly at first, and then slowly, and then quickly again at the end. The y value of the purple curve, at each value of x, is the amount of distance that we've accumulated between time 0 and time x. And this is also the area between the t-axis and the red curve, between 0 and x. In general, anytime you have a definite integral, where there is a variable in the upper bound of integration, this is called an accumulation function because it tells you how much of a quantity you accumulate between the starting point and the value of the variable.